Let's look in some detail at covalent bonding, bond formation, bond order, bond energy, and bond length. Remember, Coulombic forces in a covalent bond are directly proportional to the charge and inversely proportional to the square of the separation distance. We can see that there are repulsive forces between plus and plus and between minus and minus operating, but there are also attractive forces, minus to plus and plus to minus, that are operating. As you move closer together, the attractive forces balance the repulsive forces, but if you get too close, the repulsive force pushes them apart. This is diagrammed here. We can see that the attractive forces are predominating as you move closer together, and then you get a kind of a maximum in the attractive forces, and then as you push closer together, the nuclei, the repulsive forces begin to predominate, and here they're so high that they'll actually push the two nuclei apart. And the atomic radius is defined at the distance at which the repulsive and attractive forces are equal. Here's another look. Beyond the atomic radius, there is a net attraction. Inside it, there's a net repulsion. The equilibrium shows where the bond is and where the radius of each atom is. There's oscillation around that radius. We call that the stretch in infrared spectrophotometry. Here's a final look. At this distance, there's inadequate attractive force. You've got two hydrogen atomic orbitals. You bring them closer together and they start to overlap. There's a net attractive force. The bond is forming. And finally, we have a molecular orbital, a bonding orbital forming here that is lower in energy than the two hydrogen atoms by themselves. As you know, there is also an antibonding orbital, but it's way up above here. And of course, the electrons would start off in the bonding orbital, the lower energy. Bond order. Bond order relates to the number of bonding electron pairs between two bonded atoms. And we're going to show you the shortcut way of doing bond order first, and then the formal way. For instance, the bond order of the carbon-carbon single bond in acetone here, or in this carbon-to-carbon bond, single bond, is 1. There's only one bonding electron pair between these two nuclei. However, if you look at the carbon-oxygen bond, you see a double bond, a sigma and a pi bond between the carbon and oxygen. There are two bonding pairs, and therefore the bond order is 2. If you looked at acetylene or ethine, you would see 3 bonding pairs, a sigma and 2 pi bonds between the two carbon atoms, with a very high electron density here in this triple bond. Now, we can look formally at bond order and define it as the difference between the number of bonding electrons and the number of antibonding electrons divided by 2. So we subtract bonding minus antibonding and divide by 2. And as an example, we can ask, why isn't helium a diatomic molecule? Well, the bond order would have to be greater than 0 for a bond actually to form. Here you see 1, 2 helium atoms, and the 2 helium atoms here combine in a bonding orbital. The atomic orbitals become a bonding orbital and an antibonding orbital. But since there's a total of 1, 2, 3, 4 electrons in the atoms, you have to put 2 of the electrons down in the bonding orbital and 2 up in the antibonding orbital. Now, let's subtract. 2 minus 2 is 0, and 0 divided by 2 is 0. The bond order is 0, so helium does not form a diatomic molecule. Now, the bond order relates to the bond length. We can imagine why. It has to do with the electron density. Higher bond order means a greater electron density and a greater Coulombic attraction between positive and negative. Higher bond order then also would mean a shorter distance between the nuclei. There would be a lower bond length. Again, because of the higher Coulombic attraction, the low energy state is for the carbon atoms to be closer together in order to take care of this greater bond electron density. Triple bonds then would have the lowest bond length. Bond order also is related to bond energy. If you have here 2, 4, 6 electrons, 3 electron pairs between the two carbons, you have a high electron density and therefore the highest total bond energy. Increased bond order means higher electron density, and it means higher bond energy. So, arrange these carbon-nitrogen bonds in order of length and total bond energy. The lowest length would be a 1, the highest would be 3. The lowest energy would be 1, the highest would be a 3. Turn the video off and then turn it back on to see the answer. Here are your answers. As you can see, the cyanide has the lowest bond length, but the highest bond energy because of the triple bond and the high electron density here. And the amine, having a single bond, has a bond order of 1. A bond length is the highest, the third, and the bond energy, of course, would be the lowest. How do bond strength and bond energy relate? Bonds, of course, do not spontaneously break or form. You have to put energy into a bonding orbital in order to get the electrons up to the antibonding orbital where they will break the bond. So the energy we must put into a bond to break it is called the bond energy or bond enthalpy. Breaking bonds is then always endothermic. You have to put energy in, usually in the form, say, of ultraviolet radiation. So bond energies, bond enthalpies are always positive numbers in the tables. Now we can use bond energy calculations, for instance, if we've got resonance structures, to help us determine which Lewis structure is the lowest energy and therefore the best and the most likely to form when there are several resonance candidates. How do bond strength and bond length relate? You can probably answer that by now. If a bond is strong, it is hard to break. Strong bonds then have high bond energies, and of course when the bond order is higher, the bond energy is high and the bond length is low. Shorter bond length then implies higher bond energy due to the increased Coulombic attraction with the high electron density. And so remember, the distance between the atomic nuclei when you have minimum energy is the length of the bond. Here is a table of bond length and bond energy. You can look at it and see as the bond length goes down, the bond order is going up, here with the carbon-carbon bonds, and as the bond length is going down, the bond energy is going up. In fact, going from here to here just about doubles, from going to here, just about triples. Same thing, it can be seen with the carbon-oxygen bonds and the carbon-nitrogen bonds. The bonds between the elements become shorter and stronger as the bond order increases. Now we can use this to solve problems. For instance, if we know what bonds are broken and what new bonds are formed in a chemical process, we just subtract the energy of the bonds we're forming from the energy of the bonds we're breaking to get a net energy input or release. Net endothermic or net exothermic. So, going back to the table, if a single carbon-to-carbon bond is broken and a single carbon-nitrogen bond is formed, what's the total change in the energy or enthalpy? Let's go back and look at the table. And now let's go back and look at the problem. And you can turn the video off and come back when you think you have an answer. And here's how we do it. The carbon-carbon bond energy is 347 kilojoules per mole. The carbon-nitrogen, the bond that is formed, is 305 kilojoules per mole. We subtract the 305 formed from the 347 broken, and we get 42 kilojoules per mole. And that tells us that the process is endothermic overall, because more energy has to be used to break the carbon-carbon bond than is recovered in making the carbon-nitrogen bond. Now, I would suggest you always put the sign on the delta H. In this case, you would put a plus on the 42. Here's another problem. I want you to read it and then turn off the video. You've got the bond enthalpies you need there. And once you've solved the problem as best you can turn the video back on and see the solution. You want to know the overall enthalpy change for the reaction, taking ethene, C2H4, reacting it with chlorine gas to form this dichloroethane over here. So figure out what bonds you have here, correspond them to the table, and go ahead and do the mathematics and check your answer. Here is the way we solve the problem. We're first going to say that the delta H is the sum of reactant bond energies minus the sum of product bond energies, or enthalpies. So we break a carbon-to-carbon double, and that's 614. We break 4 carbon to hydrogens, 4 times 413. We break 1 chlorine-chlorine at 242. We then add all these numbers together and we get 2508 kilojoules per mole. We then do the same thing, adding up the bond enthalpies for the products, 2 carbon chlorines, 1 carbon carbon, and 4 carbon hydrogens. Here's the math. The sum of that product is 2656. We then subtract the 2656 formed from the 2508 broken, and we get negative 148 kilojoules per mole. And this means that we have an exothermic process, so this energy is running downhill in a favored direction, so that when these two things react, it should be pretty easy to get the dichloroethane product.